Hello everyone, and welcome to our Chapter 2 guided notes. Let's go ahead and get started, just make sure I was recording. So we're going to start with Chapter 2 because that's really where kind of the course gets going. So let's see what we have here. We have a frequency table, and the first question is, well, what is a frequency table? And these notes will be posted online, so you'll be able to see them a little more clearly, but a frequency table measures I'm going to say counts of quantitative data as they fall into, and I'm going to say equally spaced bins or classes. All right, so that's our definition, and so based on that definition, let's see what we have here. So we have widths or bins or classes of, it looks like about 60 seconds here. And if we read through the problem, it says, hey, we have diners at a fast food restaurant, and essentially we just want to count of how many of them fall into the bins, or how many total people were in this summary. But more so what I want to explain here is that, well, what that means is there are 7 individuals. Now that could mean people or orders, depending on how you want to count it. You know, maybe you're the company and you're scanning like ticket times, and so you actually probably don't know the individual person behind that order, but you have their ticket time. And so we have 60 to 119 seconds, then 120 to 179 seconds, 180 to 239. And so what I want you to see first is that these are equally spaced bins. So once we start counting by 60, we follow that through. We'll talk about that more in a minute. And also that we have these frequency here. So if you want to know how many individuals there are, well, all you actually need to do is count up this individual data. Now for that, I maybe might use a calculator. So 7 plus 23 is 30. I know that, but then I've got the 13 and the 2 and the 4. And so I just add that up, and it looks like there must have been 49 individuals. Again, that could be checks or people. We're used to kind of thinking about statistics in terms of people, but you never know what you might be measuring. And then finally it says, is it possible to identify the exact values of the original service times? And the answer to that is going to be no, because, and maybe we can follow this up as a little note, once a table is constructed, the data within each bin cannot be, let's see here, specified within the range of the bin. Again, that's some fancy wording, but essentially, I just know there are 7 orders that took essentially between 1 minute to 2 minutes. Now, maybe it took 1 minute and 1 second. Maybe all 7 of them were right up to the literally last second, and they all were in the second before 2 minutes, or maybe they all were evenly spread within there. Maybe one was 65, one was 75, one was 85. We don't know. So, no, it doesn't tell us anything about the data between the limits, but we just know that each data within that class, each 7 of these points falls within the class limits, as we call them, class or bins. All right, up next, this is going to be kind of the vocab section, so here we go. We'll write these down. Pop those in there. Again, I know the font's going to be small here, but this will be filled out online, and you could open it up kind of after the fact and see what we end up writing down. All right. So let's talk about lower limits. And actually, you know what? I might just do this problem and then paste it online. So this is kind of, I guess I'd call it a vocab section. We kind of just have to do it once just to say we did. And the lower limits in this case would be the 100, the 200, the 300, 400, and 500, etc. So it's literally just the left-hand side of each one of those limits. So what's the lowest you could be for any of those classes or bins, again, as we called them? The upper limits, well, you guessed it, are just the other values. All right. So right off the bat, I'll go ahead and paste those in there. Oh goodness, AI is trying to help me, and I don't need AI's help. All right, the class width. This one might be a little bit tricky because you might be thinking, well, 100 to 199 is 99. But careful when you measure class width, and this might be what we write down, is class width is any lower limit to the next lower limit. We could say or upper to next upper. So in that case, what that would be for this problem is 100, because 100 is 200 is 100 away, 299 to 199 is 100 away. It's any lower limit to the next lower limit, any upper limit to the next upper limit, so each one of those is 100 away. All right, the class midpoints. This is a little bit interesting. The class midpoints are the average of each class's lower and upper limit. All right, so we can start off that by saying the first one would be 149.5, then we would have 249.5, etc., and then I'll answer that here. All right, so this is where we do, when we think about the midpoint, that's where we think about the lowest and highest within the class and then actually average those two. And this would be 249.5, 349.5. Sorry, this is so repetitive, but hey, it's good practice. It'll stick in your head better. Whoops. Whoops. Mistyped that one. 449.5. There we go. All right, up next, the class boundaries. Now, this one's a little bit interesting because if you think about it, the boundaries would be what's in between. And if I count, there's one in between here, a second in between here, a third in between, and a fourth in between, but there are actually 6 boxes. But we mostly have the right idea. If I think, what's the difference between 199 and 200? Or maybe think about it this way, what's the difference between a B and an A? Usually we would think, oh, well, if I get an 89.5, it'll round up. And actually, we're in a similar situation here. What's in between 199 and 200? Or, let's see here. So let's define it like this. Class boundaries are the average of any upper limit to the next lower limit. And so the thing about that is, again, there are 6 boxes. Again, there's 4 in between that we already noticed. So what we're going to do is we're going to identify the 4 in the middle that I have in the data, and then we're going to figure out by pattern what happens. So if you average 199 and 200, you end up with 199.5. If you do the same with 299 and 300, you get 299.5, 399.5, 499.5, and at that point you see a pattern. So this one must be 99.5, and this one must be 599.5. Awesome. And then once again, they want us to count up how many people are actually in this, and it looks like there's gonna be, I think I see 150. Again, you can use a calculator to count that out though. All right, awesome. So that's a pretty big section there. Up next, let's quickly introduce the idea of the normal distribution. The normal distribution is super important. Let me pull up a little graphic of it. All right, so I pulled up a picture of the normal distribution, and so here's some things I want to show you. First, for this picture, a minute, let me just get this big screen just so we talk about this for a second. First thing I want to talk about with the normal distribution is I want you to notice that it is symmetric. It has one peak in the center, and if you look at this kind of percentages, you can see that the closer you are to the middle, the higher percentage of data is contained in your, I guess, equally spaced bins, if you can see it that way. Now, what we're doing here is we're starting to very early on blend the difference between a purely smooth continuous data and kind of those bins that we were just talking about. In fact, if we look at this page that I pulled it from, oops, here we go. You can see here that, see this image right here, and sorry for all the ads, but sometimes the internet's better than a book. You can see that this is essentially an example of continuous data that we would have, and we've got bins and bars here with equally spaced bins. And so the idea is, yeah, what if eventually you had these bars in equally spaced bins, and you were to kind of try to draw a smooth curve between the peak of every single one of those, well, that's where you would end up with a shape like this. And we call it the normal distribution because it turns out with a lot of what we call real life measurements, it shows up all the time, or it's what you would normally expect. So we start to call it the normal distribution. Now, for the sake of what we're going to learn together, we're going to attach a few key phrases here. All right. And you'll see these in the book a lot. So the normal distribution is symmetric. All right. I won't put an exclamation point on it. Maybe we'll make a bulleted list or something, but oh well. It's symmetric. We'll also say this. It starts low. You'll see this again in the homework a lot. Proceeds to one or two peak, or I guess high values. Then decreases again. Now, again, that's just a way of describing as we read it from left to right. It's increasing. It started low. It increases to one or two high values, one solid peak essentially, and then decreases again. So that's just another way of describing it's symmetric. And then we'll say there is one peak in the middle, and we'll also say with two tails, on either side. All right. That's what we really need to say about the normal distribution. All right, it's symmetric. It has one peak in the middle and two tails on either side. And honestly, that's all we have to do there. Now, when we talk about things being normally distributed, or approximately normal is a very strict criteria. It must be very close in order to call something approximately normal. All right, so we're just going to say that early on, that you need to be almost exactly normal to be normally distributed. And let's get back to the notes and see what we find. So for this one, all right, let's see what we get here. It looks like I've got my one peak at kind of around 14, but what I'm not seeing is I'm not seeing symmetry over here. See, this side has 8, this has 5, this has 6, and this has 0. So there's like a complete dip earlier on, I guess, the left side, the lower side of the data, than the upper side of the data. And so, no, this would not appear to be normal. Not because it doesn't decrease from the max to a low. It does decrease on both sides, but it just doesn't appear to be symmetric, which I guess would be what we would say there. So watch the wording there. It's going to be a little bit nitpicky and a little bit troublesome. Now this question, by counterexample, you can see it's not exactly perfect, and that's why I'm using some choice wording there, that it needs to be very close in order to call something normal. And this one's only off by 1, right? This is 3, this is 2. Other than that, it's an exact match. It's got the one peak in the middle, and it's decreasing to the left, the lower values. It's decreasing from the right for the upper values. And so we also get these wordings in here. So it starts low, proceeds to 1 or 2 high frequencies, and then that one says increases, but that's not right. We want to start low, proceed to 1 or 2 high, and then decrease, and we want to be symmetric. Awesome. All right, up next, we're going to leave normal distribution, but it's kind of, they just want to introduce it as early as possible because really our whole entire course is going to be focused on that. And now we're going back to actually constructing these by hand. Now the thing is, we aren't going to do this by hand. We're going to utilize technology as we do this. So when you look at this question, all right, you're going to see all these data points here, and definitely do not copy them onto a piece of paper. Be ready to use some fun online tools and make your homework a lot easier for yourself. But one thing we need to do here is we need to also take note of the class width and the initial lower limit. So notice that the class width is 15, so be careful. That doesn't mean 15 goes here, because remember the width is from any lower to the next lower. So these would be my limits. So this would then be 14. This would then be 29. This would then be 44, and we'll talk more about how I know that in a second. It's kind of our one other point we want to say here. 74, then we'd have 75, and then we would have 89 if I continue that pattern. All right, so let's make another note here. We'll say creating frequency tables, and the one note we're going to put here is the upper limit should be 1, and there's kind of an interesting way to phrase this. I'm trying to make it as non-mathy as possible, but make it be true. 1 unit lower than the next lower limit, and we'll say the unit is determined by the specificity of the data itself. Specificity? I can spell. There we go. All right, so what on earth do I mean by that? Well, let's look at my data. My data only has a tens place and a ones place. And so because I only have a ones place as the most specific I get with my data, that's why I decreased by 1 to the next lower limit. So if I had tenths or hundredths, if I had hundredths, right, if I had like 0.84, 0.32, then this lower limit would be 0.499 because I would go to the specificity that my data showed. So because, again, my data only went to the ones place with no decimals, I'll decrease by 1 with no decimals. From there, now let's see how we're going to use our fun online tools to count these frequencies up really quick. We can actually press this little button right here, and we can say open in StatCrunch. And StatCrunch is a feature that you actually get on your exams. Now, when you open StatCrunch, you'll see the data gets copied into like the first column, and the column is kind of already labeled var1. And we can then just say, I want to make a histogram. All right, and we'll learn why it's a histogram in a second, and that's actually kind of the next section. But they said they wanted us to start at 0 and have a width of 15, so that's all I need to type. And again, it's var1. That's the only column I have. And take a look at that. There's my data. So there's 5 values, then 13, then 12, 9, 5, 1. So let's hear 5, 13, 12, 9, 5, 1. So there we go. 5, 13, 12, 9, 5, and 1. Awesome. All right. It says, does the data appear to be normally distributed? Well, let's see here. There's only one side to the left before the peak, right? The 1 or 2 high values. So there's only one value on the left of the peak. There's 3 values on the right of the peak, in those equally spaced bins. I guess not values, but you know what I mean. 3 separate bins on the right-hand side of the peak, but 1 bin on the left side of the peak. That is not symmetric. So we'll say no, because it's not symmetric. Even though it went low and then high and then back to low, it wasn't symmetric. And then we get some other questions here, and I'll tell you this, I would love to stick to the math and not do these extra questions, but this is part of statistics, so we won't always go through all of these. Part of that will be for you to learn and explore, but we're going to focus on the math side. But don't sleep on these parts of the questions because, again, they'll show up in your exam questions as well. So let's see here. Is there anything unique about this data? Let's look at the data again. So we're talking about commute times to work for people 16 or older. And let's see here. If we look at all the data, all right, just take a look. And now let's read through the questions here. It says the data are quantitative but are actually categorical. What does that mean? It means your data is a number, but the number actually, like least to greatest, doesn't matter. Kind of like your phone number, right? If your phone number is greater than someone else's, that doesn't actually mean anything because it's kind of just random digits. Other things like this will come up, a basketball jersey or, a player's number on their shirt. That actually doesn't matter, or your license plate, right? Even though license plate has numbers, its order, like alphabetically or numerically, doesn't mean anything about you being more or less. But Commute times, those are quantitative. That actually measures something where, 4 minutes, everyone would love to have a 4-minute commute. No one wants a 60-minute commute. We know what that means when we talk about commutes, and we know that those numbers are meaningful and their distances from one another actually have impact. Let's see here. An unusually large value of 80 appears to be an error. Well, let's see here, and we'll take a look at this in the next section. But let's look at that StatCrunch graph again. Well, the thing is, this data value, even though it's only one very high frequency, it is next to the rest of the data. There's not a what we call gap in the data. So we wouldn't necessarily say that this is unusually large, although it is large, but there's no gaps. And then again, based on gaps, there appears to be two different populations. Well, no, because I just said there were no gaps. Finally, most of the data are rounded to 5 or 10 minutes, so maybe they're estimates. And if I look at that, that actually appears true, and that kind of makes sense, because usually when we say how long it takes us to get to work, we don't say, oh, it takes me 37 minutes. No, we'll just say it takes me 30 minutes or 40 minutes or maybe 35 minutes. But usually we don't say the exact amount. So it looks like that was the true statement there. Okay, we're not going to go through all these, but take a look. This time, they're actually just really close together values, so 0 through 4. So this time, your scale would actually just be those exact values. And this would actually almost be more of a dot plot if you think about it this way. We actually have the exact values. We're not creating bins. We actually do have, from this table, you could actually reconstruct the entire values, but just saying that, and then we'll skip on. Up next, look at this. The width started, or the bin lower limit started with 40.0. And if I look at my data, I see that they go to the 10th place. So again, not to do your homework for you, but this would start at 50.0. And that means this would be 49.9, because since my data went to the 10th place, or one after the decimal, my upper limits should be one less than the decimal, or one after the decimal less than the next lower limit. All right. Once again, this is more so a dot plot if we kind of think about it that way. And finally, we have a cumulative plot here. So let's just see what that is. And you really just have to follow the wording. So how much is less than 40? Well, less than 40 would be 35 to 39. There's only one data value there. Now the next is less than 45. Now less than 45 is the 40 to 44, but it's also the category before, the class before, 35 to 39. So now there's a total of 4 values. So you can kind of see a pattern there that at first I had 1, then I added the 3 more and got up to 4. So then I would add the 5 more and get up to 9. Then I would add the 13 more and get up to 22. Then I would add the 9 more and get to 31, so on and so forth, 38, and 39 in total. So we call that a cumulative distribution plot. All right, we're doing good on time. I think we can go ahead and open up your second homework assignment, 2.2, and continue. All right. Up next, we're going to kind of talk more about the normal distribution. So 2, we'll just say more on histograms and the normal distribution. Histograms. All right. So one thing we can say is, if data is not normal, it may be, we'll say, skew left or skew right. And we'll say skew left is when the data has a left tail longer. We'll just say to the left. We'll just say has the left tail, actually. And then we'll say skew right is when data has a right tail. Now, what do we mean by that? If I could draw a little quick picture here. This would be skew left. So you can see the majority of my data here falls to the right. And let me just erase that one part. Whoops. So again, it's as though my whole entire data distribution looked like this right here. Maybe I don't have to draw that line in there, but it just kind of stops. Now skew right, and again, just to show you this, is there doesn't always have to be like a peak, so to speak. Maybe it would look like this. That would be skew right. So where the tail is, right, we said there's a peak and then some tails. So if you have one longer tail than the other side, where the tail is, if it's on the left side, left tail, or right side, right tail, that's how you call it skew left or skew right. Okay, if adult male heights are normally distributed and we select a random sample and create a histogram, well, we would expect it to be bell-shaped, because if it's normally distributed, we know that the normal distribution looks like a bell curve. All right, whoops. Up next, let's see here. If we only have 5 data values, I'm going to leave that question to you. I think you can do it, but essentially, you can't do too much with 5 data points, no matter what shape you want to make. This histogram, how many members are included? Again, you just count the heights. So it's just like a frequency plot, only instead of looking at tables, we're looking at the graph after. So 1 plus 4 is 5, 5 plus 1 is 6, 6 plus 1 is 7, and 7 plus 3 is 10. So you're just counting the height of each bar, and that's how many people there were. Because again, each bar now is the same thing as one of those classes, and each one of those classes has a width. So we're just translating those frequency tables into graphs. So maybe that's one thing to say, is to go back and make a new slide. We could say, histograms, what are they? Histograms are graphical displays of frequency tables. One thing we can say is bars in a histogram, whoops, I can't spell that today. Bars in a histogram should touch, right? We could see that here. And that's because, or we'll say since, in a frequency table, the bins are always equally spaced and next to each other, so to speak. Right, when you looked at those other tables before, let's go back real quick. Right, we went from 100 to 199, and then right after we went to 200. So there shouldn't be necessarily a visual space there. We should put them right next to one another. So we can see that here. This one went from 110 to 130. If you think about that, then actually we went probably from 110 to 129. And then the next lower limit is 130, which actually answers our question. My class width is, well, the distance between these two, which looks like it's 20. So from 110 to 130, so on and so forth. All right. For the first lower limit, hey, it looks like I was thinking ahead. The first lower limit looks like it's 110. And the next upper limit, well, let's see here. It's probably going to be 129, since all of these are counting by single digits. I don't see a 0.0, so I probably shouldn't do 129.9. All right, cool. Up next, we have the actual data, and they want to get the frequency. Now, one thing I want to show you is, of course, you could open this up in StatCrunch directly, and you could just actually ask to make the histogram like we did before. We could say start at 0 and have a class width of, I think it was 15, but I moved a little quick. So I could already see the plot right there. And yep, there it is. But really, the question is, do you need to? Because if you have this table, we should be able to just kind of say, hey, 4, 14, 13, 9, and just look at the first few of these. So that looks like about 4, and then 14, 13, 9. This one also looks like that, but these two don't. This doesn't look like 4 and then 13, something 9. And neither does this one. This is like 4 and 4. So it's definitely A or B. And then the last question is, wait a minute, look at this bottom axis here. This is going from 1 to 60, but 0 to 60. This is going from 0 to 90. And if I look at my data again, this is going up to 90. So now I know it's C. All right. So you could use StatCrunch, but you don't have to. And also, let's see here. This has a longer right tail to review what we had there. Longer right tail, and so the distribution is skewed right, and that means it doesn't appear to be normally distributed because, well, we literally just said it's not symmetric, right? That's another way of saying it's not symmetric. It has a longer right tail than it has a left tail. based on all that, I think we can skip this one other than just to say, hey, look, the bars are touching in A and B, and the bars are not touching in C and D, and they wanted a histogram, so guess what? It definitely can't be C or D. Hopefully you catch that. Up next, similar question. Hey, look, this definitely looks skew right. Definitely has a longer right tail, but careful, it goes 21. That's about 26. Careful, count those axes carefully. They're counting by fives. So there's the one that starts at 21. So already that's not too bad to get. And then let's see here. Is this from a normal distribution? No, it's definitely not symmetric. It's skewed to the right. All right. With that, I think we can move on. Bars in a histogram, touch. So that's 2.1 and 2.2, and I'll see you for 2.3 and 2.4.